大家好，我是王不老说半岛。Hi, folks. Today I'm going to continue my discussion about hybrid bonding interconnect, HBI. Today my focus will be on patterns, process controls, and mention how I use chatpdf to cheat a bit. That'll be fun to discuss that. Let's proceed. Give you a quick refresher. Hybrid bonding, forming and process challenges, shown this in this Betsy folio is very nice, very nice. It talk about you have to prepare your die surface in a very clean and active manner. If you like to be, usually like it to be hydrophilic, so as they could attach to each other easily. And there are two bonding that happens. One is the so-called dielectric bonding. It's pretty much SiO2. Sometimes they use other material, but the mainstream is SiO2. It's easy, and then it's has a lot of experience on that. People sometimes use silicon carbide or some other material. Some has even carbon nitride. Some we'll talk about that in one of the photos. And then you want to connect the copper. The copper has to be able to form a concave a little bit lower than on the outside, lower than the electric edge. So as when they form, they will form a kind of small bubble. But that's intentionally they want to do that because this way they would have a better chance of a good alignment. The good alignment here is better than if you protrude out. If you protrude it out, right? Imagine you have a concave manner that connects each other. Then that concave will squeeze. You make it bigger, right? And make it bigger is not good. You will lose the mechanical tolerance. You will reduce the scaling. And after that, you gotta get rid of this bubble, right? This void. Then you are near it to a certain high temperature, 150 to, less than 300. Hopefully you could anneal the all the voids off. And sometimes it's hard to remove that 100%. So if a little bit void, that's probably okay. As long as you don't impact the integrity of the final results. That the shear strength and all kind of mechanical property after you're near it. Remember, this is done by van der Waals. This contact is a van der Waals force. And here it becomes covalent bonding, which is quite strong. As long as you ensure that the bonding is very covalent, as close to theoretical value as possible, then you're fine. And that is the bound strengths, okay? And then you would like to have a void free, of course. That's ideal world. Whether you get that, that's a different story, right? So today, as I mentioned, we're going to talk about a lot about patterns, all right? So the first pattern I would like to introduce is that I try to find what is the first pattern about HBI, hybrid bonding. And it turns out that, according to what I read, the story is that the electronics. It turns out there are a couple of key players in a series of inventions. Finally, they form a company called Electronics. That Mr. Enquist and then Fontaine and then Mr. Ton, all these key guys that they they were developing hybrid bonding at RTI. RTI is in North Carolina, right? That's a very famous research center there. And initially they called it Z bond, right? It was nickel and oxide. And then eventually they figure out that this technique can also apply to the very important one, the copper, right? It was initially called direct bonding interconnect, right? And people eventually figure out that it's not just the copper bonding, right? It is the hybrid of copper bonding and the SiO2 bonding. So that's why it's hybrid, right? You need two bonding. The electric bonding and then it's copper bonding. You have two bondings. So that's why it's hybrid. And since we're going to talk about a lot of IP, and then I want to know what are the key players in this IP concerning about the hybrid bonding. And then it turns out that the knowledge Nomad, this consulting company, IP company, they did a good summary. This is 2019, and look at the number of forward citations, right, versus the number of citing the patent portfolio. So they figure out, I mean, they summarize it. It turns out there are 290 hybrid bonding patents in 2019. And of course, right now in 2023 is much more than that now. The picture that interests me is the comparison between TSMC and Intel. You can see that TSMC is, you know, pretty ahead of Intel from this perspective. And Xperi, this is the famous IP company. They keep, churning out a lot of IP. Right? So they are the biggest player. People use this technology eventually had to buy some IP from. I think that's bottom line. So just keep up. I want to give you a high level picture about the all the key players. And I don't see the Samsung here. They probably hidden somewhere, but you can see that the Global Foundry, IBM, Intel, all these are in this side, and then TSMC is the only foundry that is ahead of everybody else in a quite a big gap. Okay, and recently the IMAX, this is a famous packaging conference that discuss the progress of everybody. Betsy, they come out, and then this gentleman did a good summary that he probably went to this conference, and then he mentioned about the three key process. Since I'm going to talk about process control, right? I want to see what are the problems that the key tool vendors like Betsy is facing and what are their solutions. And that's my goal. I hope I could, I would like to share that with you. The first thing they mentioned is CMP dishing, all right? Ensure proper thin barrier thickness and the barrier height is lower than SiO2 profile. Okay, that the bottom line, they are talking about the topography here. They need to make sure copper is lower. So, and to make that happen, you have to rely on CMP. So CMP play a key role in ensuring the profile of the copper and the dielectric is what you want. Sometimes you will see that in some special case, which I'm going to mention later, sometimes they actually want the top copper to be this way, to be higher than the outside. So then we will see what's happening, okay, in the later foils. But this is what they say, right? This is a POR process. Copper thin layer has to be, and they have a thin layer, they have to be lower than SiO2. You don't want the thing. The issue is this: you don't want this to be dishing too much. If you say, "I want to do this," can I do that? Well, that's not good because when you form a big void, if you form a big void that big, there's no chance for you to close it. You have to increase the temperature to very high, and if you go to about 300, usually you got into trouble, right? Because everything's starting to move around. Remember, the device down here, all right, they have the backend of process already. Now, these are all device, and they have a lot of backend process, which maximum temperature is like 450. So if you're pushing to 3 to 400, it's not going to be happy. They're not going to be happy. So this means that the void here has to be as small as possible. So you could use a lower temperature to get rid of the void by copper interdiffusion. All right. So this is what I meant. So it had to be lower, but cannot be lower too much. And then for the high volume manufacturing perspective, cleanliness is key. Any particle on the bonding surface, you will poor adhesion, weak bonding, complete bond failure. This is a challenge for dice wafers. And they will see that the Betsy did reasonably good job here, but the EVG, the other supplier, had problem. They couldn't overcome this problem. All right, so then the yield is low. Okay. The plasma activation, the bonding, they find out you need to, as I show in here, you have to passivate the surface first. Okay, you have to passivate your, especially this inorganic material, SiO2, something like that. You have to passivate it in a way so as that they would, in a surface, form some kind of hydrophilic bonding to help you bond. So, hydrophilic surfaces, so you could help to bond. But that plasma activation effect, it will degrade with excessive Q time. Q time means that the moment you finish the activation and then the time to actual bonding could be minutes, could be seconds, could be, I don't know. That time is called Q time. You queue up and wait. And that Q time is too long, then the effectiveness of the plasma activation, you put some chemicals, you do something to the surface, that effect is actually a unstable effect. It's not a thermal equilibrium effect. And that will degrade as a function of time. If you have excessive Q time, then that defeat the purpose of activation. But if you do too much, say PR process is bombarded with some kind of plasma, right? And plasma activate the surface, it clean and activate at the same time, pretty nice. But if you do too much, they will rot. They become rough. Okay, it kills the surface. In that sense, you got problems, right? You got problems. You degrade, you create voids. It roughens the surface and then degrades the bonding. So this is the current process challenges that face the big vendors, the big tool suppliers. Just want to give you a high level feeling of that. So now they go to a little bit more details. What happened at agrobonding? These pictures, reflect to what we saw previously in this foil, right? The kind of three stage, right? Surface preparation, bonding, and then annealing. And then these three stages can have multiple mechanisms going on inside here. And what's interesting me, I'd like to convey to you is what is the initial driving force when they bond during the bonding? It actually is the pressure gradient. And she actually did a good modeling. So he's using this modeling. What he did here is to simulate the process with a kind of a sinusoidal wave, right? It's a wavy surface. As we shown here, it's kind of a wavy. That's what he assumed because he needs to mathematically simulate it, right? And here the cavity here will be forming like this. That's the void. And then you have a contact start to form, right? And then this is the copper start to bond here, and then you squeeze the copper pillar to squeeze out. And then what happened here is that is the diffusion of the materials, and that diffusion of the surface diffusion of the material, which is called copper atom, is called surface creep, which means the surface deform, right? From this, you are pressurizing it with certain force, right? The force here, okay, is about, in Betsy tool, it's about, say, 20 Newton, something like that. And then you apply a force, and then you start to squeeze, and then you start to squeeze this, okay? And this squeeze at a certain temperature, Then you wish you could activate the copper atom diffusion on the surface. So surface deform. You don't want it to do too quickly. You don't apply too high a pressure here. If you apply too high a pressure, you get into trouble. So that's what I meant. He hopefully in a finesse manner. Somebody did the comparison to pressure centering, and then they found there are three sources material transfer, the how copper atom moves. Surface source is surface one, they initially the void, and then they become a oval shape. Okay, and then there are three types here, in the interface source, bulk source. All right, so all these three sources you have to control in a process way that at the end of the day, you want to have a micro creep, not a macro creep, because macro creep means that it deforms too much. The whole thing deforms too quickly, meaning that this also deforms. Right? You want a local deformation, a microscopically deform in a way that you would like to control it. Okay. If you go to too much force, then you go to macro creep, and that macro creep create a distortion too quickly. Then you lose the process control window. But on the other hand, you don't want way too long. I said, okay, I could do slowly, right? I could slowly touch it and then squeeze it slowly. But that slow down the whole process. I want throughput time, small throughput time. I want 2,000 die per hour. Tell me, if you do only 200 die per hour, I won't buy your tool. Okay, so that is the challenge. That's one key challenge. And then I want to touch in a way that I have very fine control, about less than, say, 100 to 200 nanometer sigma control. So this is where the headache comes in. Okay, you want to control everything in a nice manner, in a finesse manner, but swiftly. Okay, so if I use Betsy's own tool, the 8800 Chameo Ultra Plus. Okay, they claim it's HVM, and then it's a 22 development, 2022 development. It's in high volume now, very nice, blah blah blah. But you look at it. Look at the key competitive advantages. At the end of the day, this is what they can offer, right? 200 nanometer accuracy, and then a 2,000 unit per hour. So this is what they hopefully the control head can do. This is called Van Gogh bond head. All right, open it up. This bond head, press it down carefully. This bond head push it down to the substrate. This die here for the substrate, and this has to be all actually kind of a floating. Right? You don't want to attach to anything because you want able to adjust something in a way they're all complete parallel to each other. So this is a camera. So these are very delicate cameras, okay? And then it will keep sensing it while you're lowering down your bond head to touch the substrate die. You want to attach them together. It requires a super fine control, right? This old camera had to be within it kind of helicopter landing down. Had to be controlled very nicely. Otherwise, it crash. Right. So very careful. And if you look at the environment, they have a lot of control of that. They use air N2 flow to push the bond head down in a nanometer control manner. And everything is had to be inert gas, right? You don't want to oxidize your copper. And there's oxygen control at less than 100 ppm. And your die transfer, everything had to be kind of a floating, right? In a way that you could adjust everything. And then you have to adjust your substrate temperature, your hot pedestal. When you're bonding, actually, you are doing this so-called a pressure bonding, okay? Which means that you creep at certain high temperature. This high temperature is not that high. For 150 for dielectric bonding, less than 300 for, or a little bit higher for the copper bonding. Okay, so that's what you want to control in a way that give you 200 nanometer accuracy, high speed, 2,000 units per hour. All right, with this kind of a schematics to show you the flavor of it. And it turns out very few companies will can do that properly. Let's look at the difficulties. Right, the difficulty one from the machine process control perspective is that you need to have alignment control sigma, I don't know, at less than 100, say 100 nanometer roughly, right? And then you can see that they use all kinds of camera schemes. The camera has to be very good. You have to exceeding diffraction limit. You have very good fiducial form and sizes, and you're calibrating at the same time to yourself, right? So you're taking a picture and then aligning your top die to the bottom as you are flying a chopper, and keep running down, keep watching it, and keep adjusting your flight speed and all that, right? And that's you adjust everything on the fly. So that is quite a challenge. So I would say that extremely delicate and fast fingers. So imagine you have your finger forcing this down and putting on the bottom die, bottom substrate, and then the you have to be very quick and very delicate at the same time in a nanometer manner. Now let's say 100 nanometer scale. That's the first challenge. All right, so it's alignment control sigma. And then the second is you need to reduce the mechanical and electrical noise. Imagine you are running a lot of mechanical motion here, right? A lot of mechanical thing is moving in and out. They are all driven by certain motor. A motor can generate electromagnetic field, and that will perturb a noise. That will generate a noise, right? Magnetic field eventually can induce eddy current and can do a lot of crazy stuff to make your fine control not so fine. So to achieve uh, such a fine control 100 nanometer scale, you have to do a lot of grounding, right? A lot of good grounding and then the shielding. So your machine has to redesign pretty much, at least enforced by certain new grounding. Like new grounding is super important, right? It is one of the biggest challenge. And if you look at all these shielding technique in a textbook and online, the new metal, they call it new metal, which is blocking the magnetic field. So this component will not touch that, will not affect the other component. You have special new metal. New metal is special alloy that will actually absorb all the magnetic fields that are going through them. So you need a shielding of the signal wire in a separate source from the noise, reducing the amplitude and then twisting the signal wires. These are simple stuff, but they are actually more than this. There's some delicate stuff that every vendor know about their tools, that they do specific twists to make sure their tool are grounding well. And then the key components inside will show it. So when they have a delicate motion of forcing this pop plate down, will not be affected by the noise that comes from the system. So they say this is what they have. This is what they say. This is what I have with the noise X and Y position. Now, if I did a good noise reduction, I got 3x better. It was 150 nanometer, and then I dropped to 50 nanometer sigma or 3 sigma. So this is what they can improve by simply taking care of machine grounding. I myself did a lot of experiments myself, and grounding is one of the big concerns in many of the tools we have, because tools are so complex. And they can talk to each other if you don't take care of the grounding issue and shielding issue. Okay, so that's the control part. So if you look at what we just discussed, I can give you a quick summary of process sigma control. The overall steps are not too complex. They're only 3 steps, right? This is what you have. Pretty much 1, 2, 3. This is what you do within one tool. It's not too big problem. But the devil is in the details. We want superfine control of physical positioning between the die and substrate wafer without electrical noise. Okay, grounding and shielding had to be well done, and so as that I don't have any. I have to have a minimum electrical noise. At the same time, I want a high throughput. I want to do everything quickly, and then low COO cost of ownership. So, so you want everything, right? Yeah, you want everything. So this is a quick summary. Now let's go down to what a process guy can do, right? What a process guy can do. What they can do in terms of improving these three simple process. We come back to the same process. The three simple process. What a process guy can tweak to each of the process that make the overall high yield. Okay, so this is what we try to do. Try to do. Okay, quickly. Before we go, I forgot to mention this one. Houston got a problem. This is EVG in the IMAC meeting, which I mentioned earlier. This is Betsy's summary. They talk about difficulties, right? What they have. This is Betsy's perspective. If you look at the other one, their problem is probably very obvious. They say their wafer to wafer bonding, okay, pretty good, mature. They could do one micron pitch, fine. And then the die to wafer bonding, they got a problem. Process equipment maturity is starting to yield, but still many difficulties. And they could do 9 micron. Okay, this means that 9 micron is pretty okay, but anything that less than that, they got problems. Their yields, and then they have a yield issue pretty much. Okay, so this is what they're working on. I think everybody probably working on this. Die to wafer, you go into smaller and smaller die, thinner and thinner die. Your mechanical requirement, all right? Your mechanical requirement, and then it's a big problem. Electrical noise, once you solve it, probably okay. But this mechanical, physical control is so delicate that I think that's where the challenges are. And from the process guy, well, I can't change the tool, but what I can do is change some material and some process on the material onto the material. So that's what I can summarize for you here. Okay. First, silicon carbon nitride cap, and then the 111 nano twin copper. Okay. Better plasma activation, and a warpage reduction, HOE reduction. All these are currently many guys, many experts, they provide their expertise, try to improve the overall scaling, and then the overall HBI process technology. And here is SIN cap, SICN cap on SiO2. This is what I proposed. Okay, what I have in mind is that the top wafer, they make it slightly protruding out. And bottom wafer is wider and slightly recessed. Okay, here is recessed. Here is sticking out. This is different from what we said here. Here we want both recessed, a little bit lower than the outside. But I may say, no, that's not good enough. This is what I want. I want top to be a little bit sticking out and bottom a little bit recessed down, with the caveat that the top is smaller than the bottom. So when I land, I have a good landing. I can always have a good landing, right? And then I could reduce the copper pad, the height of that, and that could help me scale it. And then I also proved that the anneal temperature can be lower. So this is what they propose. It's kind of a pretty good idea. They published in 2017. I don't know which one adopted, but I mean it's pretty good novel ideas. This is, I think, pretty decent, pretty good. Okay. But my question is that, well, not my question, they mentioned themselves, is silicon copper nitride, copper CMP is critical. You need to form something like this is not an easy thing because SiCN is deposited on top of SiCN, on top of the SiO2. And then you have to polish in a way that some of them recess, some of them sticking out in a well-controlled manner. Wow, that's not an easy job. Okay. But that's the idea. All right, so now look at the other idea. Okay. That's first idea. Let's look at plasma activation. This is a recent paper by Kane in 2021 in this journal. I think it's interesting. All right. So you have many things you can activate. You have the argon, O2 plasma, and then you dip in the acid, HCOH, your vinegar, pretty much. And then you have a formic acid for the copper. Okay, so you have many different type of activation. I call it cooperative activation. The plasma, and then you have the SCOS, you have the formic acid, right? So all these things, you could do a better activation. What's a better activation does? They actually lower your annealing temperature. Remember, previously we mentioned that this anneal temperature is like, 300, 300. But they said they could lower it to 200 because they make a surface much more sensitive, much more easy to bond, much easier to bond. And that's the end result is your anneal temperature. Okay. All right. So that's the idea. Whether you're going to do that, I don't know. But the idea is there. So the foundry would take this idea and run with it, right? Meaning that I could do a better job. I could twist my plasma, okay, at different power, and then I could dip into acid. I don't know. You can do that HVM, but that's the idea and then formic acid. So all these recipes can help the foundry to test and then the tool supplier to test. If they find out really helpful, they might incorporate these ideas into their tool sets, right? So that's what JDP is about, the joint development plan, right? Then there is a nano twin copper, okay? They find out this, if you could do it, pretty good. What I meant pretty good is that they actually have a much higher thermal diffusivity than the regular one. People find out that 111 oriented nano twin, a lot of twinning, a lot of defect. This means that they are defect, right, done by electrochemical deposition. If they are fine grain, it helps you a lot. And it has a very high surface diffusivity. Right? And very high surface diffusivity means that it's easy to deform. Let's go back to this picture. So when you touch two copper together and you squeeze them, and then they will start to creep. This creep is a surface creep. You don't want to do a bulk creep. You want a surface creep. The creep requires the surface atom, copper atom, to move. That is the surface diffusivity. So the quicker it moves, the better, isn't it? So you want a material that can move pretty quickly. I mean, a specific copper that could move quickly. And then 111 claimed to have a surface diffusivity 3 order to 4 order magnitude higher than the 100 or 110. Okay, yeah, that's pretty scary. Okay, scary good. But can you do it? Well, it turns out, yes, you can do it. That ECD, a certain type of ECD chemistry will give you naturally a lot of 111. It's not 100%, right? It's not 100%, all 111, like 80%. That's pretty decent already. And then, and on, you using this method just published in last year, that they find out that their specific contact resistivity go to E minus 9. This is crazily good, okay? It's pushing to the limit of copper bonding. And if you look at the other type of material, give you probably 1 order less. So yeah. And then they say I could do it in a lower temperature. Right? Except at low temperature, you require longer time, which is not good. Okay. Which you could do it, say, in seconds. But they turn out in minutes or longer to achieve that. So it's an idea, right? It's an idea. And then that give you something to do to improve your process. And also it reduces wafer warpage. It turns out this material, okay, if you've done it right, they figure out it could reduce the warpage in a way. All right, so this is how they did experiment. They put material together and then try to different shape the die, a different shape of die, either concave or convex, something like that, and they squeeze it and they study the voids, and then they find out that the voids at the wafer edges will increase. This is distance from the wafer edges. Okay, this is the wafer to wafer. This is another experiment, right? They study wafer edges, which is the kind of a warpage effect that somehow at the edge of the wafer, this is the edge of the wafer, you got the highest number of voids. It's because of stress. Pretty much just stress. And then the nanotwin copper can help solve that problem to some extent. They're probably not the only one to solve the problem, but they help, right? So this is they try to use this one to demonstrate that improves. But it's not good enough? Still not. Maybe not, right? The famous formula for wafer warpage, they calculated from the intrinsic stress and thermal stress. Okay, so this is a formula that's well known, calculated from the Stoney equation. Okay, and so bottom line, this copper has the higher surface diffusivity. They move quickly on the surface, so easy to get rid of the voids. And then the contact resistivity is pretty nice. And then they could also reduce the wafer warpage a bit. So they're pretty decent, pretty good. Okay. Whether going to be cost reasonable and then fast and then meet all the other criteria that remain to be seen, right? And then we are moving to the wafer warpage issue. Here, wafer warpage, you easily to form voids. The reason, this is one reason they mentioned, because SiO2 bonding is not perfect. Okay, your bonding during the wafer, the binding mechanism, if the surface oxide initially, right, is wavy structure, right, wavy structure, the oxide bonding, the difference, and this is your surface treatment. This surface treatment by your plasma activation, and initially it's about 12 angstrom thick, and with a anneal, you hopefully could form a nice bond like this. It become a regular SiO2 bond, right? This is a SiO2 bond, a regular, and it's about 3.2 angstrom. So this is a covalent bonding. This is not. This is still a roughly a van der Waals bonding. It's very weak. You don't want a weak bonding. Weak bonding, the die could just move by itself. You don't want that, right? So the bonding, hopefully, is directly you want to achieve. Okay. So that's what I said. Don't forget about the SiO2 bonding. It's critical too. If you have bubbles, right, especially wafer to wafer, then you're in deep trouble, right? The yield on the edge of wafer will be lower. And then, as we know, last time when I mentioned, you want the yield to be 100%. You cannot lose the wafer edge. That's not good. Each die you put it on is a non-good die that costs a lot of money, right? So how to reduce that? So I searched some of the patterns that probably could be of interest to you, right? And this one is the methods of minimizing warp in production of electronic assembly. And then this is the patent number. They have this weird structure. And I don't have time to read all this IP paper, actual IP PDF. They are actually difficult to read, right? Yeah, it's a lot of legal jargon that try to confuse you. And you have to understand technically so as that you can understand what they're trying to say. I wrote 30 patents myself. I know that. After I finished my patent writing, my lawyer would tweak it in a way so nobody else can read it properly except them. Okay. So I use chat PDF cheating. I cheat. So I throw this PDF, okay, I mean, throw this IP into PDF, into chatgpt.com and ask them to analyze it. This is what they explained to me quickly. And then I quickly cut the idea. So that's why I cheat. He says that the method involves arranging a dielectric and conductor layer symmetrically above horizontal plane of symmetry so as that overall it could have a force balance to reduce the warpage effect. And then in matching the thermal expansion, the coefficient of CTE, coefficient of thermal expansion, various systems. All right, so that's, of course, you want to expand your IP, your pattern as broad as possible. So you do something to address the thermal expansion coefficient issue. So this is what this IP was about. But I think a better one is this TSMC one. TSMC one is say, oh, this is my process. All right, this is my process. I have a wafer, and then I have a deep trench capacitors from the front side, and then I have a stress inducing from the back side. Wow, they have two layers, and then and then after that they form a compressive dielectric layer over the devices. Okay. And this is what they, on the first page, oh, they put something here, something here. Then, so what is it about? I cheat again with chatpdf. So they try to, okay, the tensile material exerts stress on the backside of the wafer, and then the compressive form over the in front of the wafer. So the tensile, the bottom one, this one's tensile and top one's compressive, and they would do it in a way that will complete balance each other out. So I have a flat, stress-free wafer. That's pretty good, decent idea. Right? By balancing the stress on the front and back side of the wafer, the structure reduced wafer ball substrate wall. Nice. Okay. I think this is one they use. That's the key advantage of TSMC over the other guy. They in the wafer to wafer bonding, this is this is what they actually I think this is what they actually do to make sure they have don't have warpage problem. And about the die to die, that I don't know. Probably do something too there too. That would be interesting to see. Okay. So this pretty much summarizes what I try to present in this talk. Is about four patterns from the beginning of the Ztronics and then later the TSMC patterns and process control. How fine a physical process control we need to do in order to have HVM type of tool available to us. And then I cheated with a chat PDF just for the fun of it. Okay. And I hope it's good to you. Thank you very much.